Hi, good morning everyone. Today I would like to share with you lecture 11. That's the new chapter, Laplace transform and the definition, inverse and the ROC, the region of convergence. And this is the last chapter of this topic, Laplace transform. So you have cover lecture 11, 12, and 13 for the chapter Laplace transform. So in this lecture, we'll cover the introduction. So what is the Laplace transform? What is the definition? Okay, by using the formula. And the type of the Laplace transform, that is the unilateral and the bilateral. So two types. And how to find the inverse of Laplace transform and how to draw the region of convergence. That's the ROC. Okay. Okay, class, do you know what it is? Who is he? Okay. So he was Pierre Simon Laplace. Okay. If you look at our chapter, it's called Laplace transform, and his name was the Laplace too. So this means that this person, this Laplace, okay, developed the Laplace transform. Okay. And he was born in 1749 and passed away on 1827. So it's how old was he at that time? Yes, it's about 80 years old. All right. So what he said, what we know is not much. What we do not know is immense. Means that, yeah, it's correct. What we know is not much. We only know a little bit things only. Okay, just a surface. And what we do not know is immense. It's like a sea. It's huge. Okay. So what is indicate? This indicates that we must, we must study more to enhance our knowledge. So the transformation of the Laplace was first proposed by this Pierre Simon Laplace in 1780 and later adopted for various engineering applications to solve the differential equation. That's why this transformation is called the Laplace transform. Okay, Laplace transform actually is a generalized continuous from the Fourier transform. So where the complex sinusoidal become the complex exponential in the form of exponent negative st. So where the s can have any complex value. Okay. Later I will explain more in the s domain. Okay. So Laplace transform actually is to convert the integral and differential equation into an algebra equation. So now let's look at the type of the Laplace transform. As I told you just now, you have Laplace transform has two types. So unilateral and the bilateral. So if you, from the words of unilateral, you know that it's only for one side. Okay, it's a one-side Laplace transform. So it's used in the causal system, designed for feedback and control system. Okay, so the effect of the pulse is included in the form of initial condition at t equal to 0. Okay, so for bilaterals, bi means it's the two sides, so it's a two-sided Laplace transform. Suitable if no information exists at t equals 0, so initial condition unknown. And this is useful for the study of stability and causality. Now let's look at the bilateral Laplace transform into details. Okay, for bilaterals, the integration is from negative infinity to infinity. So that's why it's called bilateral, right? And okay, xt exponent negative st dt. So let's look at the first one first. This one is what? This is the Laplace operator, like a L. So Laplace transform of the xt. This is in time domain. Xt is your signal. B is referred to the bilateral. Okay. So Laplace transform of xt is your signal, equal to xs. So this is already, after Laplace transform, you get xs. So this is in the Laplace transform is in the s domain. So equivalent to the integration minus infinity to infinity that is obtained from the b here, and xt your signal exponent negative st dt. So the variable s is called S domain or Laplace domain and is denoted by S. And it broken into real and real and imaginary part. And it's written as S equal to sigma plus j omega. Okay, sigma plus j omega. Okay. So from here, this one we know that the time domain changed to the S domain, so you know that it's a Laplace transform. Okay. So for a bilateral, it won't straight away from minus infinity to infinity. It may separate into two. This means that it's from minus infinity to 0, okay? And then from 0 to infinity. So it can separate into two. Even though it is from minus infinity to infinity, but it's separate into two. Okay, so it's a plus, it's a summation. But it's quite different from the unilaterals. Okay, unilaterals is straight away from 0 to infinity, so the positive side only. 0 to infinity xt exponent negative st dt. So the t is more than 0. The t is more than 0. So we call it as a unilateral for the one side only. Okay, now let's look at the relation of the Laplace and the Fourier transform. Okay, if you still remember the Fourier transform is integration from minus infinity to infinity, xt exponent minus j omega t dt, right? Okay, if you look at the Laplace transform, is the exponent xt multiplied with the exponent negative st dt. So you change the j omega to the s. So actually the s is a complex, as mentioned earlier, is a complex. So complex means that it's a sigma plus j omega. Actually, it still remains the j omega here, but this j omega it will refer to the imaginary part, and the sigma is the real part. Okay. So if we take out the exponent negative sigma t from the exponential, we left the exponent negative sigma t, exponent negative j omega t dt. So we can say that this xt exponent negative sigma t, this is the Laplace transform, is generalized from the Fourier transform. Okay, so this part is a Fourier transform, so generalized from the Fourier transform. Okay, class. Now let's look at the example. Okay, determine the Laplace transform of the following continuous time signal and their ROC. Okay, so xt, if the signal xt is equal to AUT, so determine the Laplace transform. So xt equal to AUT. So what is UT? UT means that it's the t from 0 to infinity. So t more than equal to 0. So Laplace transform of xt is the xs. Okay, you use the, by definition, so you use the formula. So minus infinity to infinity, xt exponent negative st dt. And you know that the limit is from 0 to infinity. So you change the limit. Okay, you change the limit from 0 to infinity, and you substitute the value of the xt is the a, and you have the exponent negative st. Okay, so a is the constant, you take it out. Okay, so you integrate for exponent negative st dt. So after the integration, you get the exponent negative st divided by negative s. Again, this a and negative s actually is a constant. Okay, it's a constant, so you take it out. And then you substitute the value for the infinity and 0. Okay, here bear in mind that there's two conditions. For s more than 0, for s less than 0, because if you look at this, we do not know that what is the value of the s. So we have to assume where either the s is more than 0 or the s is less than 0. Okay, so we assume for the two cases. Let's say if s is more than 0, okay, s is more than 0, we substitute exponent negative, and then s is positive value, so it's negative t. It's a negative t. So t is infinity, right? We substitute for infinity. So exponent negative infinity, and then minus with 1. Okay, so exponent negative infinity, we get 0. Okay, we get 0. So you have negative a over s multiplied with negative 1. So you get positive a over s. Okay, you have the value for s more than 0. If s less than or equal to 0, here we substitute with the negative. Let's say s is negative 1. If negative and negative 1, so you get positive value. So positive infinity. So positive infinity, you won't get 0. Positive infinity, you will get infinity. So everything you minus with 1, infinity minus with 1, you still get infinity. So for less than 0, you will get infinity value. So this is, you get a two answer. Laplace transform of a ut, you get a over s for s more than 0, and for infinity for s less than 0. And the question also asks you to plot the ROC. So ROC is to the right of the line passing through the sigma equal to 0. Okay, this is the ROC. So I think later section will teach you on the rules of the ROC. Okay, I will teach you more in detail in the later section. Now, let's go to another example in which how to find the Laplace transform for the signal xt equal to 1. Okay. Again, we use the unilateral only. You use unilateral. So we substitute the value of the xt equal to 1. So you get the 1 here, 1 exponent negative st dt. So you integrate, you get exponent negative st over negative s. Again, you have two conditions, either more than 0 or less than 0. Now, let's look at the s that less than 0. If the s is less than 0, okay, so you have negative, let's say negative 1, positive, negative, negative 1, and then t substitute infinity. So it's a positive infinity. So positive infinity is a infinity. Okay, if you look at the s is more than 1, so means that the s is positive. So exponent negative, there's a positive value, and the t is infinity. So negative infinity, you will get 0. So bear in mind that exponent infinity, you will get infinity. Exponent negative infinity, you will get 0. So you have the value of 1 over s. Okay, you understand, class? Okay, never mind. We go to another example. We show how to find the Laplace transform again. Okay, let's strengthen your basics. Okay, if you look at this example, so you substitute the xt is the exponent at. Okay, substitute with the xt is exponent at. Now you have the a minus s. Okay, a minus st. From 0 to infinity, we are using the unilaterals. Okay, you have the, after you integrate, you get exponent in the bracket a minus st over a minus s. Again, we need to test for the s, right? So a minus s equals 0, s should be equal to a. So we test for the s more than a and s less than a. Now, if s is less than a, okay, let's say s is 5, a is 10. So a minus s should get the positive value. So here we get the positive value. So exponent positive a minus s infinity minus with 1. So you get infinity. So if s is more than a, means that if s is 5, a is 3, so a minus s, you get negative value. When you get negative, so it means that it's the exponent negative a minus s infinity. So you get exponent negative infinity, which is equal to 0. So 0 minus 1 multiplied with 1 over a minus s, you get 1 over s minus a. Okay, class? Do you understand? Okay, next we go to another example. Find the Laplace transform of the xt equal to negative xt equal to exponent negative at ut. So how to solve this question is just like a previous. Okay, can you hear me, class? Okay, now let's look at this example. Find the Laplace transform of the xt equal to exponent negative at xt, ut, sorry. And then you know that this is Actually, this question is same as previous question, just that just the input xt is slightly changed to a negative value, okay, negative 80. So negative 80 ut, we know that it is from the 0 to infinity. So again, we use the definition. By definition, that is a 0 to infinity, exponent 80, exponent negative st dt. Okay, so you multiply in, you will get exponent negative s plus 80 dt. Okay, so this one we need to test 1 over this, if after integration is 1 over negative s plus a, so this one we will test it. So negative s negative a is equal to 0, so s is equal to negative a, so we need to test for the s more than negative a and test for the s less than negative a. Okay, now we look at how to test for the s more than negative a and s less than negative a. So if s is more than negative a, this means that let's say x is equal to 5 and a is equal to 10. So whether s is more than negative a, so we check. S is 5, x is 5, and negative a is 10, so negative 10, so it's correct. S is more than negative a. So we substitute the value, negative s minus negative a equal to negative 15. So this is what we don't get we don't want the value here. We just want either it's a positive value or negative value. So it's a negative value. So it's a negative value. Okay, it's a negative value. So okay, from just now we have what? 1 over, after the integration we get negative s plus a, and you substitute the value is exponent. Exponent, you have the negative s plus a t 0 to infinity, right? So we substitute the value, negative s plus a, and then this part we get the negative value. Am I right? Just now you get the negative value, so your exponent negative infinity, we substitute the value of t here, and then substitute the value of 0, so minus exponent 0. So this one you will get 0, so 0 minus 1, so this one is part 1. Okay, you get 1, so 1 over negative s plus a, you get 0 minus 1, so you get positive value is 1 over s plus a. Okay, there's another case. If s is less than negative a, so in what condition? The s is negative a. So let's say s equal to 5 and a is equal to negative 6. So we try 5 and negative, is it correct? Negative 6. So s is less than 6. So this is correct, right? S is negative 6 is correct. So we check negative s, negative a. We get is negative 5, negative a. So this is what? Negative 5 plus 6, so it's a positive 1. So we get the positive value. We get the positive value. We only want the positive or negative only. We don't want the value. We don't want the 6 here. Okay, we just want to know whether it's a positive or the negative value. Okay, now 1 over negative s plus a, and then exponent negative s plus a is positive value, so it's a positive infinity minus exponent 0, so you will get infinity. So here we know that you get for s more than negative a, you will get a value is 1 over s 1 over s plus a. For s less than negative a, you will get infinity. So this is how you get it like this. And then for the ROC, the x-plane you have for the ROC, you have the imaginary and the real part. So you still remember S is sigma plus j omega. So sigma is a real. Okay, j omega is a imaginary. So this is we call it S-plane. So S more than negative A, okay, is the ROC. We sketch the ROC is S more than negative A. This is the ROC, is a value there. We go to another example. That is find the Laplace transform for the xt equal to cos omega t. So cos omega t, we change using the Euler formula, change the cos to the exponent. So that is the exponent j omega t plus exponent minus j omega t divided by 2. So Laplace transform of the cos omega t, okay, you're using the formula for the unilateral from 0 to infinity. We substitute the value of the exponential part here. We take out the 1 over 2. That one is the 2 is a constant. Okay, 1 over 2 is a constant. And then multiply with the exponent negative st dt. Okay, so we multiply in part by part. So you have plus here. Let's say you have the exponent negative st multiply with exponent j omega t. You get negative s plus j omega. Okay, t. dt, and then plus with the another half exponent negative st multiplied with exponent negative j omega t. So we get this part, negative s negative j omega t dt. So we integrate, so negative s minus j omega t, we integrate, you have divide by negative 1 over s minus j omega. This one also the same. So integration, I think integration you should have no problem. So once you've done the integration, you multiply in. You substitute the value of infinity and a 0. So in this case, we assume for the s is the real part. The s is more than 0. So you have substitute the exponent negative. This part we assume is a positive value. So exponent negative infinity. So you will get 0 here. Okay. So we won't have the infinity part lah, because we all assume it's a positive value. Alright, so this one you get 0 minus 1, so you multiply in, you get 1 over s minus j omega. And then you have this part is negative 1, you multiply in this one, you have the positive, so positive 1 over s minus j omega, multiply with 0.5. So you get this part. So in order to do this, because the different denominator, we multiply with another denominator. So s minus j omega multiply with s plus j omega. Okay. So so we identity the denominator. So s squared minus j omega squared. So as you know, j squared is equal to negative 1. So that's why we get s squared plus omega squared. And then s plus s is 2s, negative j omega, plus j omega minus j omega. So we get cancel out. So the answer is s over s squared plus omega squared. For the s is more than, this is r is a real. For s is more than 0 only. So that's all for the example of the Laplace transform using by definition. Okay, now we go to the next one. So in your slide, also also attach a Laplace transform table. Okay, for the xt and what will you get for the xs. So this table is in your slide. Okay, in which I will share later. And the next subsection is the inverse Laplace transform. So inverse Laplace transform, okay, you want to change the xs into the xt, so you get the inverse Laplace transform. So inverse Laplace transform of the xs is 1 over 2 pi j. Okay, xs exponent positive st ds. Okay, it's not dt anymore because you are originally you are in the s domain. You want to change to t domain. Okay, the time domain. And then bear in mind that the exponent st is not negative st. Okay. Okay, now let's look at the example for the inverse Laplace transform. Okay, inverse Laplace transform. If you have the xs is equal to 1 over s plus 1, s plus 2. For the real part, the s it should be more than 1. Then you need to find the xt. So we need to use the inverse Laplace transform to get the xs from to xt. Okay, the easiest way to find the inverse Laplace transform is what? Do you know what? What's the method? Yes, partial fraction expansion is the easiest one. So xs, you change to the a over s plus 1 plus b equal to plus b divided by s plus 2. Then you find the a and b here. Here, I believe that the partial fraction expansion is quite common to you, in which the a is s plus 1 divided by s plus 1, s plus 2. The s it should be equal to negative 1. Okay? So you get 1 over negative 1 plus 2. You get 1. B is s plus 2 divided by s plus 1, s plus 2, in which the s is negative 2. You get negative 1. So A is 1, B is negative 1, and you substitute into the xs, into this one here. So you get 1 over s plus 1 minus 1 over s plus 2. So from here, xs, you can change to the xt. Okay, how? Just now I show you, you have the Laplace transform table, right? So you can use this Laplace transform table to change to a xt. Okay, you have 1 over s plus s plus 1. Okay, you can check to the Laplace transform table. Okay, let's go. 1 over x plus a, okay, is your s domain. Okay, just now it's 1 over s plus 1. So 1 is the a value. Okay, so 1 over s plus 1. The xt is the exponent negative xt. So you can change to the exponent negative at. Okay. So now here is the exponent. The a is 1, right? So it's exponent negative t. Exponent negative t ut. And then for the s plus 2, the a is 2, so exponent negative 2t ut. So that's all you solve for the inverse Laplace transform using the partial fraction expansion and change to s domain to t domain. You use the you use the Laplace transform table as a guideline for you to change to the time domain. Now we go to the last part of the lecture is the region of convergence, the ROC. So what is ROC? What is ROC? The value of the S-plane for which the Laplace transform converge, we call it as a ROC. So you look at here, from the previous example, it can be seen that the Laplace transform xt have the condition to exist. We call it as a region of convergence. So ROC is a region in the S-plane. So just now I told you this one is the S-plane, in which the x-axis is the real and y-axis is the imaginary. Okay, is imaginary axis. For the ROC, we need to draw the ROC. We need to sketch, we need to sketch the ROC, region of convergence. So there are a few properties to determine which part is the ROC. So property 1 say that what? The ROC of the xs consists of the strip parallel to the j omega axis in the s-planes. Means that is the parallel strips to the j omega axis. J omega is the y-axis. So the property 1 is the ROC should be parallel to the j omega axis in the s-plane. Okay, second property. The ROC does not contain any poles. Pose means that what? What is pose? Now now let's look at the zero and pose. Okay, in the S plane, in the S, you know the S plane, the real and imaginary plane, we indicate the close as a pose denominator. Okay, indicate the roots of denominator. For zeros is we use the circle to indicate the roots of numerators. Okay, let's look at the examples. Find the Laplace transform and the ROC of the xt equal to exponent negative at ut. So this one is a previous example in which the xt is exponent negative at ut. We get the xs is 1 over s plus a. Now we want to plot the ROC. So the real part is s more than negative a, right? This is from the previous. Okay, so in order to find the ROC1 is parallel to the j omega axis. So s more than negative a. So this is s more than negative a. So the at the right of the right hand side. Okay, is the ROC is the right of the rightmost pole of the xs. Okay, let's study about the ROC of the rational function of S. You have the case 1 is the right-sided causal signals. So let the xt be the right-sided signal defined as this one. Xt equal to the exponent negative a1t ut plus exponent negative a2t ut plus exponent negative a3t ut, in which the negative a less than negative a2 less than negative a3. So the Laplace transform of this one is this one. Okay, this one is nothing lah. Just to tell you, the Laplace transform of this one is this one. Okay, the pole of the SS is what? This is the pole. P is you have 1 over s plus a plus 1. So P1, the first pole is the negative a1. So s equal to a1, negative a1. So pole 1 is negative a1. So pole 2 is equal to negative a2. And pole 3 equal to a3. So poles is the indicate the root of denominator. Okay, and zeros is the numerator. So in this case, the s plus a1, that is the denominator. It's a pole. So you have 3 poles here. Okay, what I want to show you is, okay, just now you have 3 poles, right? Negative a1, negative a2, and negative a3. You have 3 poles, but the ROC of the causal system should be what? It's the right of the rightmost pole of the xs. ROC is the right of the rightmost pole. Although you have 3 value, 3 pole value, but you take the rightmost pole. Okay? The rightmost pole. Let's say if case 2 is a left-sided anti-causal system. Okay, it's still the same example, just that the same example is like, for example, you still have the negative a1, negative a2, and negative a3. Let's say you have 3 poles value, but you will take the leftmost pole. Okay, you will take the leftmost pole. So ROC is an anti-causal system. Because it's anti-causal, for the left-sided, we take the leftmost. We won't cross to another. We won't take a2, negative a2, and negative a3. We won't cross it. Okay. So this one will cover ROC2, ROC7, and ROC8. Okay, another example is xt equal to exponent at u negative t. So this is the for the left hand side, right? You see the negative t for the left side. So you have the xs is 1 over s minus a. Okay, but for the ROC is, you won't go the right hand side because it's u negative t. So it will go to the left hand side. Okay, you go to the left hand side. So this is parallel to the j omega axis. The ROC is, this one is 1 and 5. Later we go to the ROC 5 and see what is that. Okay, for property 3 of ROC, if xt is of finite duration, is absolutely integrable, then ROC is the entire S-plane. So what do you mean? So for example, determine whether the negative infinity to infinity 7/2 t squared plus 4t ut is integrable or not. So if integrable, so means that is a the RC is entire S-plane. So you need to test. So you test the HT, you test this, you test this value, the whole value, the xt, whether it's the integrable or not. So you integrate it. Okay, you integrate from 0 to infinity, you integrate the whole things. Then if you get infinity, that is not integrable. If you get value, that is integrable. Then the ROC would be the whole entire S-plane. For ROC property 4, if xt is right-sided, then if the line for the real part is in the ROC, then all the value of s for which the real is more than the sigma will also be in the ROC. Just like this one. Okay, this is to the right. Okay, right-sided signal. Also the property 4. And for B, that one is the left-sided signal. It's property 5. Actually, I mentioned in the handwriting notes also. So property 5 is a left-sided, okay, left-sided signal, and the ROC is at the left half plane. So for the property number 6, if xt is a two-sided, that means that the ROC will consist of a strip of the strip in the S-plane that include the line of the sigma naught. Means that if more than and less than. Okay. Okay, this figure clearly shows that this is the right side plane for property 4. Okay, to the right side. And this is B is a left-sided plane, so it's property number 5. Property number 6 is in the middle. Okay, it's in the middle. Property 7 is if the Laplace transform x is of the xt is rational, then the ROC is bounded by the pole and extend to the infinity, and no pole in the ROC region. So pole is not allowed in the ROC region. And ROC property number 8 is if you have the few value, okay, in the S-plane, choose the right of the rightmost pole. If you have at the a few value at the left-sided plane, then the ROC is the left of the leftmost pole. So this is the one. Okay, this is the, let's say this is the S-plane, and then if you have two value, let's say you have two value, okay, two value here. So this is the close, so it's a pole value lah. So it's a pole value. If you have two pole value and choose the pole value at the rightmost, okay, the right-sided sequence, so it's a rightmost. So this one is the, if you have two value, if you have the left-sided signal, that means that you choose the value which has the leftmost. And then this one is a two-sided. Okay, this one is a two-sided signal. Not more than n. Okay, not more than the right-hand side. Okay, let's look at the example. Okay, this example is 1 equal to s plus a. For the Laplace transform of the xt, you get 1 over s plus a. So the ROC is more than negative a. So more than negative a is the ROC is at the right hand side, more than negative a. So this is covered in the ROC property 4 and ROC property 1. ROC property 4 means that it's at the rightmost, and the ROC number 1 it should cover the j omega axis. Okay, now let's look at the second example. for u negative t, just now it's ut, okay? So now it's a u negative t. So u negative t is at the left-sided signal. For left-sided signal, the ROC is at the left-hand side. Okay, so S is less than A, left-hand side. So this is included in the ROC number 5 and also ROC number 1. Okay. And then we look at this one. U exponent negative AT UT and plus with the exponent negative AT U negative T. So just now you have A and B, right? So now it's a combination of 2. Okay. It's a combination of 2, this one. For 1 over S plus A, the real one is more than negative A. So this one, more than negative A, the ROC is like this. And plus with 1 over S minus A. And the ROC is less than A. So it's in the middle. It's in the middle. So this is which ROC? This is ROC number 6. Yes, it's ROC number 6. And the J is also include the J omega axis. So it's include also ROC1, property 1. Okay, now we look at the representation of a pole and zeros in the S-plane. Consider the rational function of the S shown below. Find the zeros and poles of the rational function of S. Here you have the xs equal to like this. Then we can find using the root of quadratic to find the S value. Or you can use the calculator to get the quadratic function. That is S equal to negative 3 plus J2 and negative 3 minus J2. Okay. So you have this 2S value. And then next you have get these 2. So we can substitute in here. Okay, just now you find the root of quadratic is for this part. Now you already factorize this into the complex number, right? So you get this one. And then from here, you have few numbers, okay? Few 0 and poles. So S plus 2, S plus 5. So numerator is what? Numerator is for zeros. Denominator is for the poles. So S plus 2. So S equal to negative 2. So Z1 is negative 2 and Z2 equal to negative 5. So this is the zeros value that you can plot in the S-plane. Okay, this is the S-plane. Z1, so zeros is using the symbol of 0. And poles, you can use a symbol of cross. Okay, so Z1 is here, negative 2 and negative 5. And the poles value is the S. Okay, you use the symbol S. Okay, so S, you get a value of 0. And then S equal to negative 3 plus 2J. Negative 3 plus 2J. So negative 3. P2, you have negative 3 plus 2J. So this is closed. This is the P2. And then for P3 is S equal to negative 3, negative 2J. Negative 3, negative 2J. So this is P3. Okay, with a cross symbol. So this is how you plot the 0 and pole value in the S-plane. Now we look at another example. Consider a signal that is the sum of the real and the complex exponential. So xt equal to 3 exponent negative 2 tut minus 2 exponent negative tut. And then plot the ROC. So from here we can find the Laplace transform of the xt. You get xs. Either you can use the by definition or you can using by property. So for easiness, we can use the by properties if you know how to use. Property, if using property or using table also can. Okay, so 3 exponent negative 2 tut, if using Laplace transform table, you can get 3 over s plus 2. Okay, and then minus with 2 is a constant, and then exponent negative tut, so you get 1 over s plus 1. So this one is the operation of minus, and then we don't have the same denominator. Therefore, we multiply s plus 2 multiply with s plus 1. So you have 3 multiplied with x plus 1 and then minus with 2, s plus 2. And then we simplify it. Okay, we simplify it, we get s minus 1 and then s plus 2 multiplied with s plus 1. So this part will be the zeros. Okay, numerator will be 0. Denominator is called poles. Okay, then we can plot in the S-plane. Okay, this is we call it S-plane. Consists of the real and imaginary part. So s minus 1, so s is equal to 1. Here we put a circle at the 1 to indicate as a 0. And then we have pole value s equal to minus 2 and minus 1. Minus 2 and minus 1. So we need to plot the RC. The question requires you to plot the RC. So RC, okay, you have 1, 2 value. Okay, 1 and 2 value. What should we do? Okay, for according to the ROC 1, we need the j omega axis. According to the ROC 4, the signal is at the right sided. Okay, and ROC number 7, is it? Okay, so ROC property number 2 and number 7 also mentioned that no pole is allowed in the ROC. So this is, which one is pole? This is pole, this is pole. So no pole is allowed. So you only can start from here to the right. Okay, you are not allowed to start from negative 2. Okay, so no pole is allowed from the property 2 and 7. And then property number 8 states that it should be at the right of the rightmost pole of the axis. So it's starting from negative 1 to the right hand side. So this is then you sketch it. So this is the sketching part. The sketch part is the ROC part. Okay, hope you can understand. By combining those property of the ROC, you know how to plot your ROC. And then another example, consider a signal that is the sum of the real and complex exponential. So this is the complex exponentials, exponents. This is the exponent with the sign, cos ut. So plot the 0 poles of the S-plane. So from the Laplace transform table, exponent a minus at cos bt, you will get s plus a, over s plus a squared plus b squared. So you directly get from here, convert from here. Okay, the a here, what is the a value? A value is 1. A value is 1. For the cos is b value is 3. Okay, so the root of the quadratic, you have this one, right? The root of the quadratic is what? The lower part, the denominator. So root of the quadratic is s squared plus 2s plus 10. Then either you can calculate from the formula or using the calculator, you get s plus 1 minus 3j, s plus 1 plus 3j. Okay, and then substitute into this equation. Okay, substitute it into this equation. Then you get this one. So from here, since you have the operator again, so cannot. So we must equalize the new denominator. So you multiply s plus 2, you multiply with this part, s plus 1 minus 3j, s plus 1 plus 3j. For this side also same, you have to multiply with s plus 2. Okay, so this is the part that do the operation. And then we simplify and you get this one. 2s plus 5s plus 12 over this s plus 2, s plus 1 minus 3j, and s plus 1 plus 3j. With this complex, with this value, we still unable to plot. Okay, we are still unable to plot the pole and zeros. So we must solve this root of quadratic first for the numerator part. Okay, again we solve it and we get the value here. And then we must solve it until we able to get the individual s value. Like this with a complex value, that's fine. If this one is a real number also can, but you cannot have the s squared plus 5s plus 12. That cannot. Okay, so we must solve it until we get the exactly s value. So the zeros here, we look at the upper part, numerator part, zeros we get negative 1.25 plus 2.1 j. And then is minus 1.25 minus 2.1 j. That is the zeros for the numerator. For the denominator is everything here at the lower part. For the pole, we have the minus 2 and we have negative 1 plus 3j and negative 1, negative 3j. So we can plot it in the ROC plane. Okay, just like Z1 and Z2. Okay, negative 1.25 plus 2.1. So negative 1.25 plus 2.1. Okay, so we get a circle here. This is the Z1. And Z2, negative 1.25 minus 2.1. So you get Z2. For the pole 1 is negative 2. Okay, negative 2. Okay, is here, pole 1. And P2 is negative 1 plus 3j. Negative 1 plus 3j is here, P2. Another one is negative 1, negative 3j. You get P3. Okay, so this for the ROC, which one you should, how to plot your ROC? Okay, ROC state that the ROC property 1 is should include the j omega axis. So it must have this j omega axis. And then property number 2, if you have property 2. Okay, what is property 2? Property cannot include any poles. So let's say P1 and the P2 and P3. So you cannot include, let's say this one. This is left-sided or right-sided? So this should be the right-sided lah. Okay, this is the right-sided signal. Okay, how to know this right-sided? Because it's a UT. It's UT, so it's a right-sided signal. So definitely we cannot include the P2 and P3. So you should start from P2 and P3 here. So one line to the right-hand side. Okay. So property 4 also talk about the right-sided signal at the rightmost. Okay, so don't forget we also have the inverse transform of this XS. So we then plot the zero plot pattern and sketch the ROC. So given XS, okay, given XS, we need to find what is the value of the XT. Okay, so as usual, using partial fraction expansion, we get the A and the B value. Okay, A is 1 minus 1, and then we get the zero pole plot. Okay, we get the XT first. Okay, and then from the XS, we can plot the zero pole. That is S equal to negative 1 and S equal to negative 2. So our ROC should be at the right of the rightmost pole. Okay, because it's a UT, so at the right of the rightmost pole. And last but not least, this is another example. If you have the delta t, and then if you have the delta t with UT, okay, and then you have to sketch the pole and zeros and the ROC. Okay, as you know, the Laplace transform of delta t is equal to 1 because delta t only have the value at t equal to 0. So the ROC is entire as plane. And for the another two, okay, you can do the using you multiply in. Okay, you multiply in is the operation, right? Operation of plus, so you multiply in, so equalize the denominator, and then you get the value. Okay, you cannot just left s plus 1 plus 1 over s plus 2. You give me s equal to 1, s equal to 2. No, cannot. We cannot have the operation, so we must multiply in. We don't want the multiplication operation plus here, so we multiply in. We solve the equation. Okay, you see at the end there is no operation inside, only s minus 1 square over s plus 1, s minus 2. We need to get the s value. Okay, so you once you get the s value, you can plot the zero and pole. And the last part is to determine the ROC, okay, based on the add properties of the ROC. All right, so if you look at this one, you have zeros, pole and pole here. So the ROC, okay, this one is not property 1 because it's not include the j omega axis. But this one you can insert into a property number 8, in which if you have the 2 poles, you choose the right of the rightmost pole, and also a property number 2, in which it cannot include the pole value. Okay, so this is how you sketch the ROC based on the property. All right, so that's all for the Laplace transform definition, inverse, and the ROC. Hope you can understand. This video is a bit long, but since it's all talking about the ROC, I cannot separate into two. Otherwise, you can't see the connection between each ROC. So this video is a bit long. So hope you can enjoy and understand well. All right, that's all for today. Thank you very much. Bye. See you. If you like my video, you can like my video.